if I create a dipole, and I put that dipole in an electric field, the dipole will start to rotate. Let's first talk about it, why it rotates, and then I will try to demonstrate that by making a dipole, a big one, this big, right in front of you, almost as big as the one there. So let's have an electric field, like so. And I bring in this electric field a dipole, a biggie. Here, this is the one I'm going to use for this demonstration. Ping pong balls on either side, they are conducting, and they are connected with a rod which is not conducting. And so here is this dipole. So this rod is not conducting, and this is a conducting, and this is a conductor. And let's suppose this is positive, and this is negative for now. And I'll show you how we get a charge on it. Well, the positive charge will experience a force in this direction, always in the direction of the electric field, and the negative charge will experience a force always upstream. And now there is a torque on this. And when there's a torque on this dipole, it will start to rotate clockwise. And of course, if it overshoots the field lines, when it is in this direction, the torque will reverse. It's very easy to see. And so what you will see, it's going to oscillate, and if there is enough damping, it will come to a halt more or less in the direction of the field lines. And this is something that I can demonstrate. First, I have to make a dipole of this kind. And the way I will do that is the following. This is a metal bar. This is insulator. And here is there's these two ping pong balls. The one on this side has a yellow marker, the one on that side has an orange marker. And I'm going to attach them, holding them up against this metal bar. In other words, here is this dipole. It's not a dipole yet. Metal, metal, and here is a metal bar. This is a conductor which connects them. I'm going to turn on the Van de Graaff here, and the Van de Graaff creates an electric field. So we have the Van de Graaff here, and let's suppose that this Van de Graaff creates positive charge. Sometimes the Van de Graaff creates positive charge on the dome, others can be designed to create negative charge on the dome. And remember, for now I assume that's positive. What will happen now? Electrons want to go in this direction. So this becomes negative. Protons, positive charge stays behind. So that becomes, through induction, a dipole. Because I have them connected. I have them connected with this metal bar. So these electrons can flow through this bar and end up here. Now, I remove the bar. And so when I remove the bar, I have created now a dipole. I have here an insulating thread, and I have a fishing rod. And at the end of my fishing rod, I have now a permanent dipole. With that permanent dipole, I'm now going to probe the electric field around this Van de Graaff. I could have chosen the same Van de Graaff, but there's a reason why I picked this one. And as I walk around this Van de Graaff, you will see that this fishing rod, at the end is this dipole, that the dipole always wants to go radially inwards or outwards, depending on how you look at it, of this field. So I can probe this field and make you see for the first time that there is indeed somewhere here a strong radial field going in or out of the Van de Graaff. And now comes something very interesting, which I found out this morning for the first time when I did this experiment. If the other Van de Graaff there is also positive when I run it, how do you think this dipole is going to align then if I walk into it? Will the negative ball be closer to the Van de Graaff, or will the positive one go closer to the Van de Graaff? So I give you 30 seconds to think about it. So I make the dipole as it is here. Let's assume this one is positive, this Van de Graaff. So this side becomes minus, I call that A, and this side becomes positive, that's B. I now walk with this dipole, I bring it in this field, and let's assume that one is also positive. We don't know that yet. How will the dipole align now? Will A go inwards or will A go outwards? Who thinks A goes inward? Very good. Who says A goes outward? Okay, A will go inward if the two Van de Graafs have the same polarity. So if that doesn't happen, that doesn't mean that physics doesn't work. It means the two Van de Graafs have different polarities. And we'll see what happens. So let me first then create a dipole. So here is the dipole. It's sorted out now. I turn on this Van de Graaf. So induction takes place. Remember that the yellow is pointing towards the Van de Graaf, and that the orange is away from the Van de Graaf. Okay? So I induce a dipole. Oh, I really should redo that. I don't know what happens when it... I have to remove the field first. Okay. The yellow was inside, right? Was that the way it was? Okay. Yellow inside. There we go. So now it's creating a dipole through this metal bar. And I break contact. And this should now be a dipole. Now I turn on the field of the... So if the polarity is the same, yellow will go in. I will try to swing it a little. Notice two things. It's going to line up beautifully radially, but the yellow is not in. The yellow is out. So the two Van de Graafs have different polarities. But you will see they rotate nicely. And they end up beautifully radial. And when I go all the way around here, again, they may swing a little, they may oscillate a little, but through damping they will come to a halt. And look, the field is indeed beautifully radial, and the yellow is, so to speak, on the wrong side. The two Van de Graafs have different polarities. So you've seen how we can create a dipole, and you've also seen how we often can make statements about